Hello, my name is Will Tomlins, and today I'm going to be doing a presentation over the Transmission Control Protocol, or TCP for short. So first, I'm going to talk about what TCP is. TCP is a standard for exchanging data between different devices located in the same computer network. This protocol actually dates back to 1973, where it was published by two computer scientists with the names of Robert Kahn and Vinton G. Cerf in one of their research papers. Although this is not when TCP became fully standardized. It wasn't until 8 years later when it became fully standardized. Over the years, there have been various improvements, additions, and extensions applied to the protocol, but the core of the protocol remains unchanged. So, the current version of this protocol allows two endpoints in a computer network to establish a connection that enables a two-way transmission of data. In this transmission of data, any data loss that is detected is automatically corrected. And because of this, TCP has been called a reliable protocol. Finally, TCP is located in the transport layer of the OSI model. Next, I'm going to talk about how these connections work. Like I said before, TCP allows transmission of information in both directions. Or, in other words, it means that computer systems that communicate over TCP can send and receive their data at the same time. If you want to compare this to something, think of a phone call. In TCP, the basic unit of data transmission that is used is called a packet or packets. And they are limited to a size of 1500 bytes. So the TCP software in the protocol stack of the operating system is what's actually responsible for establishing and terminating the end-to-end connections, as well as transferring data. The software in TCP is controlled by network applications like web browsers or servers, and this is done through specific interfaces. Both of the connections have to always be identified by two defined endpoints. These endpoints are called the client and server. And it doesn't matter which side takes the role of the client and which one takes the role of the server. The only thing that matters is that the TCP software is provided with an ordered pair that is unique, consisting of IP addresses and ports. Next, I'm going to talk about how TCP connections are established. And in the establishment phase, it's called a three-way handshake because, as you can see, there are 3 steps. In the first step, the requesting client sends the server a send packet or synchronized packet with a unique and random number. And this specific number ensures the total transmission in the correct order. Next, if the server receives the segment or the packet, it agrees to the connection by returning a SYN-ACK packet, where ACK stands for acknowledgement. So, including and it includes the client sequence number plus 1, as you can see on the diagram to the right. In this step, it also transmits its own sequence number to the client. Finally, the client acknowledges the receipt of the SYN-ACK segment by sending its own acknowledgement packet, which, in this case, contains the server's sequence number plus 1, as you can see on the diagram to the right. At this same time, the client can begin transferring the data to the server. Next, I'm going to talk about how TCP connections are terminated. As you already know, both sides in the connection can terminate the TCP connection at any time. There's also something called half-open connection, where one-sided termination is possible. But this diagram to the right explains the steps of the two-way termination, which is what I will be talking about. In the first step, the client sends a FIN segment to notify the server that it is no longer wanting to send data. Then it sends its own sequencing number, just as it does when the connection is established. Second, the server acknowledges the receipt of the package with an ACK segment, just like before in the establishment. And that contains the sequence number plus 1, as you can see in the diagram to the right. Third, when the server has finished with the data transfer, it will also send a FIN packet to which it adds its sequence number also. Finally, it is the turn of the client to send its acknowledgement packet, or ACK packet, including the sequence number plus 1. And this is when it officially terminates the TCP connection to the server. The final topic in this presentation is going to be over the TCP header structure and what each of them mean. Starting at the top, you'll see the source port and the destination port. The source port is what identifies the port number of the sender, and the destination port is what identifies the port number of the receiver. In the next row, we have the sequence number. What the sequence number is the number that specifies the first byte of attached payload data or is sent when the connection is established or terminated. It's also used for validating and sorting the segments after the transmission. On the next row, we have the acknowledgement number. The acknowledgement number is what contains the next sequence number that the sender is expecting. An ACK flag is the precondition for validity. The next row has 4 different components, which consist of offset, reserved, flags, and window size. The offset specifies the length of the TCP header in 32-bit words in order to highlight the starting point of the payload data. And this starting point varies from segment to segment because of variable options field. Next is the reserved component, which is reserved for the future according to the RFC 793, and it's not yet in use. This field can always, or has to always be set to 0. Next are the flags. There are 6 possible single bits in the flags field, which enable various TCP actions for organizing communication and data processing. And finally, we have the window size, which this is the field that specifies the number of bytes that the sender is willing to receive. On the next row, we have Checksum and urgent pointer. Checksum allows TCP to reliably detect transmission errors. The checksum is calculated from the header, the payload data, and the pseudo header. Next is the urgent pointer. The urgent pointer indicates the position of the first byte after the payload data that is to be processed urgently. Because of this, the field is only valid and relevant in the URG flag set. The final option, or the final component is the options field, and this is used if you want to include TCP functions that don't belong in the general header. An example of this would be if you want to define the maximum segment size. The length of the options must always be a multiple of 32. If it's not, 0-bit padding is required. This concludes the end of my presentation. In this presentation, I talked about what TCP is, how do TCP connections work, then I talked about the TCP connection establishment, next it was the TCP connection termination, and finally, I talked about the components included in the TCP header. Thank you.